Hey, today we're going to continue our conversations on magnetic force on a charged particle moving in a magnetic field. To this point, we've talked about the concept and the hand rule that tells us that as a charged particle moves into a magnetic field, we can expect that charged particle to feel force on it. And because of the hand rule, we made the argument that that force would always be perpendicular to the motion, and therefore the object would begin traveling in a circle. So let's continue that conversation and get a little more quantitative about things. So we know that this charged particle heads towards this magnetic field. Take a second and see if your left hand or right hand rule works for this. One of the questions you should be prepared to answer is, as this charged particle moves up towards the top of your screen and it enters into a magnetic field that is out of the page, you can see that the force on the particle as it initially enters the region is to the right. So take a second, confirm, is that particle positive or negative? If you predicted that it's a negative charge, then you're correct. The left hand works for this situation. If you try to apply the rule with your right hand, you'll find that positive charged particles should move in the opposite direction. So let's take a look at the formula that predicts the magnitude of the force of that charged particle. So this is what the formula looks like. Cut right to the chase here. In this formula, the F is the force in newtons. It's a vector quantity, but you'll also notice that it has a absolute value signs around the force. So we're going to only calculate the magnitude of the force using this formula. That force is going to be equal to the charge on the particle in coulombs multiplied by the speed of that particle in meters per second multiplied by the magnetic field strength in units called Teslas. So that's something new in this formula, is this unit for magnetic field strength. It's measured in Teslas. A Tesla of magnetic field strength is not especially strong. The Earth's magnetic field is like a fraction of a Tesla, just to give you some sense. A bar magnet could be, in the order of maybe 1, 2, 3 Teslas. So those are the kinds of magnetic field strengths that we're going to be dealing with. Now, the one thing you'll notice about this formula, it does have this little symbol here that we're not used to seeing. And this symbol here really goes back to the idea of the hand rule. And it says that the speed, or the component of the velocity vector, and the component of the magnetic field vector have to be perpendicular to each other. In other words, the hand rule has to work. As the charged particle enters the magnetic field, it has to have at least some component of its velocity perpendicular to the magnetic field. Now, the first case we'll look at, the velocity is always perfectly 90 degrees to the magnetic field. So if you take a look back at the, let's just go back a page here, and you'll see the charged particle traveling up hits the magnetic field that is exactly perpendicular to it because the magnetic field is out of the page. And so that's just a prime example, or the perfect application of the formula. The velocity is exactly 90 degrees to the magnetic field. And for the most part, that's what we see. And so most questions take this kind of appearance. What is the force on an alpha particle moving at a speed of 5.5 times 10 to the 5th meters per second? Perpendicular, that's the key here. And that, again, we're not going to get too fancy. I mean, there are questions where it's not perfectly perpendicular, but let's take it easy as we get used to this formula. You're going to see this term quite a bit, or a description that describes the speed being perpendicular to the magnetic field. And once we see that, then we know that we can use the formula just as it stands. So, doesn't get too complicated or even that interesting, to be honest with you. The force on the alpha particle is going to be equal to Q times V times V. All of our values are here in the correct units. The only one that's maybe a little bit hidden in this case is going to be the charge, but they've identified the particle to be an alpha particle, so we should know the charge on an alpha particle. So the force should be equal to 3.2 times 10 to the minus 19 coulombs, the charge on an alpha particle, multiplied by 5.5 times 10 to the 5th meters per second, multiplied by the magnetic field strength, which is 5.2 times 10 to the minus 2 Teslas. And if you use your calculator properly, round it to the correct number of significant digits again, the absolute value of the force is going to be 9.1 times 10 to the minus 15 newtons. And in terms of direction, if we want to assign a direction to this, and we will at some point, but right now we're just looking at the formula, we would get the direction using the hand rule. So if they described or gave us a picture of the actual direction of the alpha particle relative to the magnetic field, we can make a prediction on which way the force is. But the formula itself will only tell you the magnitude of force. So that's a basic application of the formula that governs the force acting on a charged particle moving through a magnetic field. For this video, I just wanted to keep it simple, so I'm going to stop there. And in the next video, I will talk a little bit about the extensions of this, where we can go from here. But for now, this is the new formula, force QVB.